Let me tell you about something extraordinary, a discovery so unexpected, so fundamentally challenging to our understanding of the cosmos that it has sent shockwaves through the scientific community. The James Webb Space Telescope, the most powerful eye humanity has ever turned toward the heavens, has found something that, according to our best theories of the universe, simply should not exist. This shouldn't exist, not as a figure of speech, not as hyperbole, but as a literal statement about the conflict between what we've observed and what our most successful cosmological models predict should be possible. The James Webb Space Telescope has peered deeper into the universe than any instrument before it, looking back in time to the earliest epochs of cosmic history. And what it has found there has thrown our understanding into crisis. Galaxies that are too massive, too mature, too structured for their age. Black holes that are too large, too early, too impossible to explain. Cosmic structures that shouldn't have had time to form in the young universe we thought we understood. These discoveries don't just extend our knowledge, they challenge its foundations. They suggest that something is deeply wrong with our picture of how the universe evolved, how structures formed, and perhaps even with our understanding of the fundamental nature of space, time, and matter. Let me take you through what James Webb has found, because these discoveries represent one of the most profound challenges to cosmology in decades. Let me start with the telescope itself, because understanding what James Webb can see helps explain why its discoveries are so revolutionary. The James Webb Space Telescope is fundamentally different from its predecessor, the Hubble Space Telescope. While Hubble observes primarily in visible and ultraviolet light, James Webb observes in infrared light with wavelengths longer than what our eyes can see. This difference is crucial for studying the early universe. Light from the most distant objects has been stretched by the expansion of the universe. What was emitted as visible or ultraviolet light has been redshifted into the infrared by the time it reaches us. To see the earliest galaxies, you need an infrared telescope. James Webb's primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's mirror, with more than 6 times the light collecting area. This allows it to detect incredibly faint objects that Hubble could never see. The telescope operates at temperatures near absolute zero, about 40 degrees above absolute zero, or minus 233 degrees Celsius. This extreme cold is necessary because the telescope itself would otherwise emit infrared radiation that would overwhelm the faint signals from distant objects. James Webb orbits the Sun at a point called L2, about 1.5 million kilometers from Earth. This position keeps the telescope permanently shielded from the Sun, Earth, and Moon, allowing it to maintain its frigid temperatures and observe the universe with unprecedented clarity. When James Webb turned its powerful gaze toward the early universe, scientists expected to see a gradual emergence of structure. They expected to see small, dim, irregular galaxies, the building blocks that would eventually merge to form the mature galaxies we see in the present-day universe. What they found instead has challenged everything we thought we knew. Let me explain the first category of impossible discoveries: galaxies that are too massive and too early. In the standard model of cosmology, structure forms hierarchically. Small things form first, then merge to create larger things. The first stars were born a few hundred million years after the Big Bang. These stars lived briefly and died, seeding the universe with heavier elements. Gradually, gas and dark matter collected into small proto-galaxies. These proto-galaxies merged over billions of years to form larger and larger structures. This hierarchical model has been tremendously successful at explaining the distribution of galaxies we see in the universe today. It makes specific predictions about what the early universe should look like: small, irregular, low-mass galaxies gradually growing through mergers. But James Webb has found something different. Within its first year of operation, James Webb discovered galaxies that existed just 300 to 500 million years after the Big Bang, when the universe was less than 4% of its current age. This alone was not surprising. We expected to find galaxies this early. What was surprising was their properties. These early galaxies are massive, some containing billions or even tens of billions of solar masses and stars. They're structured, showing disk shapes and spiral features that shouldn't have had time to develop. They're mature, with stellar populations that suggest star formation began even earlier than we can directly observe. One of the most striking discoveries was a galaxy called JWST confirmed to exist just 290 million years after the Big Bang. This is one of the most distant and earliest galaxies ever observed. And it's not a tiny, dim protogalaxy. It's bright, it's extended, and it shows evidence of significant stellar mass. Another discovery was a collection of galaxies nicknamed the impossible galaxies by researchers. These galaxies, existing between 500 and 700 million years after the Big Bang, contain as much stellar mass as the Milky Way. The Milky Way is a mature galaxy that has been forming stars for over 13 billion years. These early galaxies somehow achieved comparable mass in a fraction of that time. Let me explain why this is so problematic. Galaxy formation takes time. You need gas to collect under gravity, collapse, and form stars. You need those stars to produce heavier elements through nuclear fusion. You need those elements to be distributed through supernova explosions. You need the enriched gas to collect again and form new generations of stars. Each generation of star formation takes time, tens to hundreds of millions of years. Building up a massive galaxy requires multiple generations. And before all of this, the universe had to cool enough from the Big Bang for atoms to form and for gravity to start collecting matter. The Standard Model allows about 200 million years from the Big Bang before the first stars could form. The earliest James Webb galaxies are being observed only 100 to 200 million years after that. The window for these massive galaxies to form is incredibly narrow. The numbers don't work. The star formation rates required to build these galaxies in the available time are extraordinary, in some cases hundreds of times higher than anything we see in the present-day universe. The efficiency of converting gas into stars would need to be near 100%, far exceeding what we observe in any known environment. Scientists have checked and rechecked the observations. Maybe the distances are wrong, maybe these galaxies are closer than they appear, and the redshifts have been misinterpreted. But spectroscopic observations, which measure the redshift directly from spectral lines, have confirmed the distances. The galaxies really are that far away, that early. Maybe the masses are wrong, maybe we're overestimating how much stellar mass these galaxies contain, but multiple methods of mass estimation give consistent results. The masses are robust. Maybe our theory of star formation is wrong. Maybe stars could form faster or more efficiently in the early universe. This is possible, but it would require significant revision of our understanding of how stars form and evolve. Something has to give. The observations are solid. The Standard Model's predictions are clear. They don't match. Either the observations are somehow being misinterpreted, or our theoretical framework needs fundamental revision. Now let me explain the second category of impossible discoveries: black holes that are too large and too early. Black holes grow by accreting matter, gas, dust. Stars fall into them, adding to their mass. And this process takes time because there are physical limits to how fast matter can fall into a black hole. The limit is called the Eddington limit. As matter falls toward a black hole, it heats up and emits radiation. This radiation pushes outward against the infalling matter. At the Eddington limit, the outward radiation pressure balances the inward gravitational pull, and accretion stops. This limit means black holes can only grow so fast. From a stellar mass seed, say, A black hole formed from the collapse of an early massive star with maybe 100 solar masses. You can calculate how long it would take to grow to 1 billion solar masses by continuous Eddington-limited accretion. The answer is about 700 million years. But James Webb has found supermassive black holes existing just 400 to 500 million years after the Big Bang. These black holes are massive, hundreds of millions to billions of solar masses. They're too large to have grown from stellar mass seeds in the available time, even with continuous maximal accretion. One remarkable discovery was a black hole existing about 400 million years after the Big Bang with a mass of several hundred million solar masses. For this black hole to grow from a stellar mass seed would require more time than the universe had provided. The problem becomes even more severe when you consider that accretion probably isn't continuous. Black holes don't feed constantly at the maximum rate. Accretion is episodic, interrupted, variable. Realistic growth rates are lower than the theoretical maximum. The time required to reach the observed masses becomes longer, and the problem becomes more acute. How can these black holes exist? One possibility is that they grew from larger seeds. Instead of stellar mass black holes formed from individual dying stars, the early universe might have produced direct collapse black holes. Black holes formed when massive gas clouds collapsed directly without first forming stars. These seeds could have been tens of thousands of solar masses, giving the black holes a head start. Direct collapse requires special conditions, very high temperatures to prevent gas from fragmenting into stars, very low metallicity so cooling is inefficient, and intense radiation to keep the gas hot. These conditions might have existed in the early universe, but they're not common. Finding so many massive early black holes suggests direct collapse was more prevalent than expected. Another possibility is that the black holes grew faster than the Eddington limit allows. Super Eddington accretion is theoretically possible under some circumstances when the geometry of the accretion flow allows radiation to escape without pushing against the infalling matter. But this requires special configurations and probably can't be sustained for long periods. A third possibility is that these black holes didn't grow at all. They were formed with high masses from the beginning. This could happen if the first generation of stars was fundamentally different from later generations, extremely massive, leading to extremely massive black hole remnants. The first stars might have been hundreds or thousands of solar masses, leaving behind correspondingly massive black holes. Each of these explanations requires significant revision of our understanding. Either the early universe was very different from what we assumed, producing exotic objects through exotic mechanisms, or our understanding of black hole growth is incomplete. Now let me explain the third category of impossible discoveries, cosmic structures that formed too quickly. The James Webb observations don't just show individual galaxies and black holes that are problematic, they reveal a pattern. The early universe was much more structured than our models predicted. In the standard model, the early universe was extremely smooth. The cosmic microwave background, the radiation from the early universe that we can observe, directly shows temperature variations of only 1 part in 100,000. This smoothness is a key feature of the standard model, explained by cosmic inflation. From these tiny initial variations, gravity gradually amplified the differences. Slightly denser regions attracted more matter, becoming denser still. Over billions of years, the contrast grew, eventually producing the cosmic web of galaxies we see today. This process should have been gradual. The early universe should have been much less structured than the present-day universe. The first galaxies should have been small and sparse. The cosmic web should have been faint and incomplete. But James Webb has found mature structures far earlier than expected. Galaxy clusters, collections of thousands of galaxies bound by gravity, have been identified at surprisingly early times. Filaments and voids, the large-scale structure of the cosmic web, appear more developed than expected. One particularly striking discovery is evidence for cosmic noon being earlier than expected. Cosmic noon is the epoch when star formation in the universe reached its peak when galaxies were forming stars at the highest rate. In the Standard Model, cosmic noon occurred about 3 billion years after the Big Bang. But James Webb observations suggest that significant star formation was happening much earlier, perhaps within the first billion years. If true, this means the universe was converting gas into stars more quickly than we expected, building up structure faster than our models allow. The large-scale structure problem connects to the galaxy mass problem. If galaxies formed earlier and were more massive, then clusters of galaxies would have formed earlier too. The entire hierarchy of structure formation would have been accelerated compared to standard expectations. This challenges the model at a fundamental level. The rate of structure formation depends on the amount and properties of dark matter, the rate of cosmic expansion, and the primordial density fluctuations. If the standard values of these parameters don't produce enough early structure, something has to change. Maybe there's more dark matter than we thought, but other observations constrain the dark matter density tightly. Maybe dark matter has different properties, but many alternatives have been ruled out by other observations. Maybe the primordial fluctuations were larger, but the cosmic microwave background measures these precisely. In part 2, I want to explain the theoretical implications of these impossible discoveries. What modifications to our cosmological model might explain what James Webb has found? And what do these discoveries tell us about the fundamental nature of the universe? So we've established the extraordinary discoveries: galaxies that are too massive and too mature for their age, black holes that are too large to have grown in the available time, cosmic structures that form too quickly for our models to explain. The James Webb Space Telescope has revealed an early universe that contradicts our best theoretical predictions. Now, I want to explore what these discoveries mean for our understanding of the cosmos. What modifications to our cosmological model might explain these impossible observations? What fundamental physics might need to change? And what does this tell us about the nature of the universe itself? Because these aren't just puzzles to be solved with minor adjustments. They may require revolutionary changes in how we understand the cosmos. Let me start by explaining why the standard cosmological model has been so successful and why challenging it is such a big deal. The standard model of cosmology, sometimes called LCDM, lambda cold dark matter, has been remarkably successful at explaining a wide range of observations. The letters in its name summarize its key ingredients. Lambda L represents dark energy, the mysterious force driving the accelerating expansion of the universe, and CDM represents cold dark matter, the invisible mass that dominates the gravitational dynamics of galaxies and clusters. This model makes precise predictions that have been confirmed by multiple independent observations. It predicts the pattern of temperature fluctuations in the cosmic microwave background, the radiation from the early universe that carries information about conditions when the universe was only 380,000 years old. The Planck satellite measured these fluctuations with extraordinary precision, and they match the model's predictions remarkably well. It predicts the distribution of galaxies across the cosmos, the cosmic web of clusters, filaments, and voids that structures the universe on the largest scales. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, and their distribution matches the model's predictions. It predicts the abundances of light elements hydrogen, helium, deuterium, lithium, produced in the first minutes after the Big Bang. Observations of these abundances in the oldest, most pristine environments match the predictions. It predicts the relationship between the distance and redshift of supernovae, the observation that led to the discovery of dark energy in 1998. Subsequent observations have confirmed and refined this relationship. For over 2 decades, LCDM has been the consensus model because nothing has contradicted it. Every observation has either confirmed its predictions or could be explained with minor adjustments. Scientists have been confident that we understand the basic framework of cosmic evolution. James Webb has changed that. The observations I described in Part 1 don't fit the standard model. Galaxies with the masses observed at the times observed require either extraordinary star formation rates, extraordinary star formation efficiencies, or extraordinary initial conditions, none of which the standard model predicts. This puts cosmologists in an uncomfortable position. Either the observations are somehow wrong, which becomes increasingly implausible as more data confirms them, or the model needs to be revised in fundamental ways. Let me now explore the theoretical options for explaining what James Webb has found. The first option is that our understanding of star formation and galaxy evolution is incomplete. Perhaps stars formed differently in the early universe. The first generation of stars, called population 3 stars, formed from pristine hydrogen and helium without the heavier elements that regulate star formation today. Without these heavier elements, gas cooling was less efficient and the physics of collapse was different. Some theories suggest that population 3 stars were much more massive than typical stars today, perhaps hundreds or even thousands of solar masses, compared to the solar mass scale stars that dominate modern star formation. If the first stars were extremely massive, they would have been extremely luminous and would have evolved extremely quickly. Extremely massive stars live fast and die young. A star with 300 solar masses might live only 1 million years before exploding as a supernova or collapsing into a black hole. These brief, brilliant lives could have flooded the early universe with radiation, possibly appearing as the unexpectedly bright early galaxies James Webb has observed. But there are problems with this explanation. If the first stars were extremely massive, they would have produced characteristic signatures, particular patterns of element abundances, specific types of supernovae, distinctive radiation profiles. Observations have not clearly confirmed these signatures. The evidence for extremely massive population 3 stars remains indirect. Also, extremely massive stars don't fully solve the problem. Even if individual stars were more massive and luminous, building up the stellar mass observed in early galaxies still requires time for stars to form, evolve, and die. The window remains uncomfortably narrow. Another variation on this theme is that star formation was much more efficient in the early universe. In the standard model, only about 1 to 10% of available gas typically converts into stars before feedback processes, radiation pressure, supernova explosions, black hole activity disperse the remaining gas. This inefficiency is why galaxy formation takes so long. But what if the early universe had conditions that allowed higher efficiency? Perhaps the lack of heavy elements reduced the effectiveness of feedback. Perhaps the higher gas densities enabled more rapid collapse. Perhaps the different dark matter environment changed the dynamics. If star formation efficiency approached 100% in the early universe, galaxies could build up mass much faster than the standard model predicts. This would help explain the massive early galaxies without requiring changes to fundamental physics. But extreme efficiency creates its own problems. If most gas converted to stars quickly, galaxies would run out of fuel. We would expect to see many dead galaxies in the early universe, galaxies that formed their stars rapidly and then stopped. Some observations suggest this might be happening, but the picture is not clear. The second option is that our understanding of dark matter needs to change. Dark matter is the invisible mass that dominates the gravitational dynamics of the universe. It doesn't emit or absorb light, so we can't see it directly. We infer its existence from its gravitational effects, the rotation of galaxies, the motion of galaxies and clusters, the bending of light by gravitational lensing. In the standard model, dark matter is cold, meaning it moves slowly compared to the speed of light. Cold, dark matter clumps efficiently, forming the gravitational scaffolding on which visible matter collects to form galaxies. But what if dark matter has different properties than we assumed? One possibility is warm dark matter particles that move faster than cold dark matter. Warm dark matter clumps less efficiently on small scales, which would change the pattern of early structure formation. Warm dark matter would smooth out the smallest structures, potentially delaying the formation of small galaxies while allowing larger structures to form earlier. This might help explain why the early universe shows more massive galaxies than expected. Warm dark matter would favor the formation of larger structures over smaller ones. But warm dark matter creates problems of its own. It tends to reduce structure on small scales, which conflicts with observations of small galaxies and the inner structure of galaxy halos. The constraints from these observations make it difficult for warm dark matter to be the complete answer. Another possibility is interacting dark matter that has interactions beyond gravity, perhaps with itself or with ordinary matter. Such interactions could change how dark matter clumps and how structures form. Self-interacting dark matter has been proposed to solve problems with the inner density profiles of galaxies. If dark matter particles scatter off each other, they would spread out the dense central regions that cold dark matter predicts. Could self-interaction also affect the timing of structure formation? The models are complex and the parameter space is large. Some versions of interacting dark matter might help explain the James Webb observations, but no single proposal has emerged as a compelling solution. Another possibility is that dark matter has decayed or transformed over cosmic history. If dark matter particles slowly convert to other particles, perhaps lighter dark matter particles or ordinary matter, the gravitational dynamics of the universe would change over time. Decaying dark matter could potentially explain why the early universe appears more structured than expected. If there was more dark matter early on, before significant decay, there would have been more gravitational clumping, leading to faster structure formation. But decaying dark matter is tightly constrained by observations of the cosmic microwave background and large-scale structure. The parameter space for significant decay is limited. The third option is that our understanding of dark energy needs to change. Dark energy drives the accelerating expansion of the universe. In the standard model, dark energy is a cosmological constant, a fixed energy density of empty space that doesn't change as the universe expands. But what if dark energy has evolved over cosmic history? If dark energy was weaker in the early universe, the expansion rate would have been slower. Slower expansion gives gravity more time to work, allowing structures to form more quickly. This could help explain the advanced structure formation that James Webb has observed. Conversely, if dark energy was stronger early on and has weakened since, the cosmological implications would be different. The details depend on the model, but dynamic dark energy generally changes the relationship between time and structure formation. Recent observations have hinted at this possibility. The DESI, dark energy spectroscopic instrument results I discussed in an earlier video, suggest that dark energy might not be constant, that its properties might have changed over cosmic history. If confirmed, this would be one of the most important discoveries in cosmology. A time-varying dark energy could potentially contribute to explaining the James Webb observations, but the connection is indirect and model-dependent. Simply changing dark energy doesn't automatically solve the galaxy mass problem or the black hole mass problem. The fourth option is that our understanding of the early universe is fundamentally incomplete. What if the Big Bang wasn't quite what we thought? What if the universe began differently than the Standard Model assumes? In the Standard Model, the universe began with a period of inflation, exponentially rapid expansion that smoothed out initial irregularities and produced the tiny density fluctuations that seeded all cosmic structure. Inflation is a successful theory that explains several puzzling features of the universe: its flatness, its uniformity, and the pattern of cosmic microwave background fluctuations. But inflation is not fully understood. The fundamental physics of inflation is speculative, and different models make different predictions. What if the primordial fluctuations from inflation were different than we assumed? What if there were more fluctuations on certain scales, leading to more structure formation at early times? The cosmic microwave background constrains the fluctuations tightly, but only on certain scales. There could be additional fluctuations on smaller scales that the CMB doesn't probe directly. If these small-scale fluctuations were larger than expected, they could seed more early structure. This is called a blue-tilted or enhanced small-scale power spectrum. Various theoretical mechanisms could produce such an enhancement: features in the inflationary potential, phase transitions in the early universe, or other exotic physics. If the primordial fluctuations were enhanced on small scales, more gas would have collected into dense regions earlier, more stars would have formed sooner, and more massive galaxies would have emerged before the Standard Model predicts. This explanation is appealing because it modifies initial conditions rather than fundamental physics. The same laws of physics apply, just with different starting conditions. But it requires explaining why the primordial fluctuations had this particular form, and that requires understanding inflation better than we currently do. The fifth option is that primordial black holes seeded early structure. Primordial black holes are hypothetical black holes that formed in the early universe, not from stellar collapse, but from the direct collapse of extremely dense regions shortly after the Big Bang. If inflation produced regions of sufficiently high density, these regions could have collapsed into black holes before the first stars formed. These primordial black holes would then act as seeds for structure formation, attracting matter and accelerating the formation of galaxies. Primordial black holes could explain both the early massive galaxies and the early massive black holes that James Webb has found. If primordial black holes formed with masses of thousands to millions of solar masses, they could have provided the seeds for rapid galaxy formation and the cores of the surprisingly massive black holes. This is an elegant solution that connects multiple puzzles, but primordial black holes in the required mass range are constrained by various observations, gravitational lensing, cosmic microwave background distortions, gravitational wave limits. The constraints don't rule out primordial black holes entirely, but they limit the parameter space. Now let me discuss how the scientific community is responding to these discoveries. The reaction has ranged from cautious skepticism to excited speculation. Some scientists urge caution. They point out that the observations are new and may be subject to systematic errors. The methods for estimating galaxy masses from James Webb data involve assumptions about stellar populations, dust content, and star formation history. If these assumptions are wrong, the mass estimates could be too high. There's also the issue of selection bias. James Webb is finding the brightest, most massive early galaxies because those are the easiest to detect. The typical early galaxy, if it exists, might be much smaller and dimmer, consistent with standard expectations. The impossible galaxies might be rare outliers, not representative of the early universe as a whole. This conservative view counsels patience. More data is needed. Better mass estimates are needed. Larger samples are needed. The apparent crisis might dissolve as our understanding of the observations improves. Other scientists see a genuine paradigm shift. They argue that the observations are robust, that systematic errors have been checked, and that the conflict with the standard model is real. They're excited about the possibility that we're witnessing the breakdown of our cosmological framework and the emergence of new physics. This revolutionary view sees the James Webb discoveries as analogous to other moments in physics history when observations contradicted established theory. The anomalous precession of Mercury's orbit that helped confirm general relativity, the black body radiation problem that led to quantum mechanics, the missing solar neutrinos that revealed neutrino oscillations. In each case, observations that didn't fit the existing framework ultimately led to deeper understanding. Perhaps the James Webb discoveries will do the same. The truth probably lies somewhere between these extremes. The observations are significant and can't be easily dismissed, but it's too early to declare that the standard model is broken. More work is needed, both observational and theoretical, to understand what we're seeing and what it means. Let me now discuss some recent theoretical developments that attempt to explain the James Webb discoveries. Several research groups have proposed modifications to the standard model that might account for the observations. One proposal involves early dark energy, a form of dark energy that was significant in the early universe but has since faded. Early dark energy would have affected the expansion rate at early times, changing the relationship between time and structure formation. Early dark energy has been proposed independently to address another puzzle, the Hubble tension, a discrepancy between different measurements of the current expansion rate of the universe. If early dark energy can solve both the Hubble tension and the James Webb puzzle, it would be compelling evidence for this idea. But early dark energy is constrained by cosmic microwave background observations, and the parameter space is limited. It's not clear whether a single model can simultaneously satisfy all the constraints and explain all the observations. Another proposal involves modified gravity. The standard model assumes that general relativity accurately describes gravity on all scales. But what if gravity behaves differently on cosmological scales or at early cosmic times? Modified gravity theories have been explored for various reasons: to explain dark matter, to explain dark energy, to achieve a theory of quantum gravity. Some of these theories could potentially affect the rate of structure formation, allowing more early structure than general relativity predicts. But modified gravity is tightly constrained by many observations, gravitational waves, solar system tests, galaxy dynamics. Any modification must be subtle enough to evade these constraints while still significantly affecting early structure formation. This is a narrow target. Another proposal involves axionic dark matter or other ultralight dark matter candidates. These models involve dark matter particles with extremely low masses, leading to wave-like behavior on galactic scales. The dynamics are different from cold dark matter, and the structure formation history could be different. These models are actively being explored, but no consensus has emerged on whether they can explain the James Webb observations better than cold dark matter. In part 3, I want to explore the deepest implications of these discoveries, what they might tell us about the fundamental nature of reality, the origin of the universe, and the limits of human knowledge. Because if the James Webb discoveries hold up, they may not just require new physics, they may transform how we understand existence itself. So we've journeyed through the extraordinary discoveries of the James Webb Space Telescope: galaxies too massive and mature for their cosmic age, black holes too large to have grown in the available time, structures too developed for the young universe. We've explored the theoretical options for explaining these impossible observations: modifications to star formation physics, changes to dark matter properties, evolving dark energy, enhanced primordial fluctuations, primordial black holes. Now I want to explore the deepest implications of what James Webb has found. What do these discoveries tell us about the fundamental nature of the universe? what might they reveal about physics beyond the standard model? And what does it mean for humanity to confront observations that challenge our most successful cosmological theories? Because this isn't just about adjusting parameters in equations. It's about the foundations of our understanding of existence itself. Let me start by examining what these discoveries might tell us about the very early universe, the first moments after the Big Bang. The standard model of cosmology describes the universe's evolution from a fraction of a second after the Big Bang to the present day, but it doesn't describe what happened at time zero or in the instants immediately following. That period remains shrouded in mystery, requiring physics beyond what we currently understand. What we know is this: the universe emerged from an incredibly hot, dense state and has been expanding and cooling ever since. In the first fraction of a second, the fundamental forces separated from a unified state. In the first 3 minutes, protons and neutrons combined to form light atomic nuclei. After about 380,000 years, atoms formed and the universe became transparent, releasing the cosmic microwave background radiation we observe today. But the details of the very beginning, what triggered the expansion, what determined the initial conditions, what physics governed the first instance, remain uncertain. The James Webb observations might be telling us something about those first moments. If the early universe contained more structure than expected, this structure had to come from somewhere. The density fluctuations that seed all cosmic structure originate during inflation, the period of exponentially rapid expansion that is believed to have occurred in the first tiny fraction of a second. Inflation stretches quantum fluctuations to cosmic scales, imprinting them on the fabric of the universe. These fluctuations are the seeds from which all galaxies, clusters, and large-scale structures grow. The standard inflationary model predicts fluctuations with a particular pattern, a nearly scale invariant spectrum with a slight tilt toward larger fluctuations on larger scales. This prediction matches the cosmic microwave background observations remarkably well. But what if inflation was more complicated than the standard model assumes? Inflation is not a single theory, but a family of theories, each with different predictions. The simplest models, single field, slow roll inflation, make the predictions that match observations. But more complex models, multi-field inflation, models with features in the potential, models with particle production during inflation, can make different predictions. Some of these complex models predict enhanced fluctuations on small scales. If such enhancement occurred, it would produce more dense regions in the early universe, leading to more early structure formation, exactly what James Webb seems to be observing. This would be a window into the physics of inflation itself. For decades, we've had only indirect evidence about inflation: the smoothness of the cosmic microwave background, the flatness of the universe, the pattern of large-scale fluctuations. Direct information about the detailed physics of inflation has been elusive. If the James Webb observations are telling us about enhanced small-scale fluctuations, they could be revealing features of inflationary physics that we couldn't access through any other means. They could be telling us about the shape of the inflationary potential, the number of fields involved, the energy scale at which inflation occurred. This would be extraordinary, using observations of the earliest galaxies to probe physics at energy scales far beyond any particle accelerator, at times far earlier than any direct observation. But the implications might go even deeper. Some theories suggest that unusual features in the inflationary fluctuations could indicate even more exotic physics. One possibility is that the universe underwent phase transitions during or shortly after inflation. A phase transition is a dramatic change in the properties of a system like water freezing into ice or a magnet losing its magnetization when heated. The early universe might have undergone phase transitions as it cooled. These transitions could have produced distinctive signatures in the fluctuation spectrum features, bumps, oscillations that would affect structure formation. If James Webb is seeing evidence of such features, it could be revealing the particle physics of the very early universe physics at energy scales that we can never probe directly, at times so early that the universe was fundamentally different from today. Another possibility is that the universe has a more complex geometry than we assumed. In the standard model, the universe is homogeneous and isotropic, the same in every direction and at every location. On average, this assumption has been confirmed by observations of the cosmic microwave background, which is uniform to 1 part in 100,000. But what if the universe is not perfectly homogeneous? What if there are variations on scales larger than our observable universe, variations that we couldn't directly see, but that would affect the statistics of what we do see? Such large-scale variations could arise from the quantum mechanics of inflation. Different regions of the universe might have experienced slightly different inflationary histories, leading to different fluctuation spectra in different places. We would observe the fluctuation spectrum in our local region, which might not be representative of the universe as a whole. If we happen to live in a region with enhanced small-scale fluctuations, we would see more early structure than a naive average would predict. The impossible galaxies might be telling us about our particular cosmic neighborhood rather than about universal physics. This connects to the concept of eternal inflation, the idea that inflation never ends completely but continues eternally in different regions of space, spawning an infinite number of pocket universes with potentially different properties. In eternal inflation, our observable universe would be just one pocket in a vast, perhaps infinite multiverse. Different pockets could have different fluctuation spectra, different physical constants, different laws of physics. If James Webb is seeing evidence of unusual initial conditions, it might be providing hints about the multiverse, about cosmic structure beyond our observable horizon. These are speculative ideas, far from proven, but they illustrate the depth of implications that the James Webb observations might have. We're not just talking about adjusting parameters in existing models. We might be glimpsing physics at the very foundations of existence. Now let me explore what the James Webb discoveries might tell us about the nature of time in cosmology. One of the striking features of the observations is the apparent compression of cosmic history. Structures that we expected to take billions of years to form appear to have formed in hundreds of millions of years. The timeline of the universe seems to be different than we assumed. This raises deep questions about the nature of cosmic time itself. In general relativity, time is not absolute. It flows differently in different gravitational fields, at different velocities, in different cosmic environments. The cosmic time we use in cosmology is a convenient construction, the time measured by observers at rest with respect to the expanding universe, but it's not the only valid way to measure time. What if our understanding of cosmic time is incomplete? What if time flowed differently in the early universe than it does today? This might sound speculative, but there are theoretical frameworks that suggest such possibilities. In some theories of quantum gravity, the nature of space-time changes at very early times or very high energies. The smooth, continuous space-time of general relativity might emerge from a more fundamental structure that has different properties. Loop quantum cosmology, for example, proposes that the Big Bang was not a true beginning, but a big bounce, a transition from a prior contracting phase to the current expanding phase. In this picture, time extends before what we call the Big Bang, and the properties of space-time during the bounce might be very different from today. String cosmology proposes various scenarios in which the early universe had different effective physics extra dimensions of different sizes, different numbers of expanding and contracting dimensions, different relationships between what we call space and time. If the fundamental nature of time was different in the early universe, our calculations of how long processes take would be affected. What appears as rapid structure formation when calculated with standard cosmic time might reflect more complex temporal dynamics. This is highly speculative, and I'm not suggesting that the James Webb observations prove these exotic ideas, but the observations remind us that our understanding of cosmic time is based on assumptions that might not hold in the very early universe. Now let me consider what the James Webb discoveries might tell us about dark matter and dark energy, the mysterious components that dominate the universe. Dark matter and dark energy together constitute about 95% of the energy content of the universe. Ordinary matter, atoms, molecules, everything we directly experience is only about 5%. Yet, despite decades of effort, we don't know what dark matter or dark energy actually are. The James Webb observations might be providing new clues. If the early universe had more structure than expected, this could be telling us something about dark matter's properties. In the standard cold dark matter model, dark matter particles are relatively heavy compared to the energy scale of the early universe and move slowly. This leads to specific predictions about how structure forms. But if dark matter has different properties, if it's warm rather than cold, if it has self-interactions, if it was produced by a different mechanism, structure formation would proceed differently. Some of the proposed solutions to the James Webb puzzle involve modified dark matter, warm dark matter with particles moving faster than cold dark matter would smooth out small-scale structure but might allow larger structures to form earlier. The dynamics are complex, and the details depend on the particle mass and production mechanism. Self-interacting dark matter, where dark matter particles scatter off each other, would change the density profiles of dark matter halos and might affect how efficiently ordinary matter collects and forms stars. Decaying dark matter, where dark matter particles slowly transform into other particles, would change the gravitational dynamics over cosmic history. Fuzzy dark matter, composed of ultralight particles with wavelengths comparable to galaxy sizes, would have wave-like behavior that affects structure formation in distinctive ways. Each of these alternatives makes different predictions for the early universe, and the James Webb observations are beginning to constrain which alternatives are viable. The implications for dark energy are equally interesting. Dark energy drives the accelerating expansion of the universe. In the standard model, dark energy is a cosmological constant, a fixed energy density of empty space. But as I discussed in part 2, dark energy might evolve over time, and the James Webb observations might be providing hints about this evolution. If dark energy was weaker in the early universe, the expansion would have been slower, giving structures more time to form. If dark energy was different in character, perhaps a dynamic field rather than a constant, the entire history of cosmic expansion would be affected. The DESI observations I mentioned earlier suggest that dark energy might indeed be evolving. If this is confirmed, and if the evolution connects to the James Webb observations, we would have a coherent picture of a more complex dark energy that affects both early and late cosmic history. This would be a revolutionary discovery. It would tell us that dark energy is not simply a cosmological constant, but a new field with its own dynamics that might reveal something about the fundamental physics underlying our universe. Now let me explore what the James Webb discoveries might tell us about the largest scales of the universe, scales beyond our direct observation. Our observable universe is finite. We can only see as far as light has traveled since the Big Bang, about 46 billion light years in every direction, accounting for the expansion of the universe. Beyond this horizon, there might be more universe that we cannot see. In standard inflationary cosmology, the universe is expected to be much larger than the observable part, perhaps infinitely larger. The properties of this unobservable universe are usually assumed to be similar to what we observe. The same physical laws, similar fluctuations, similar structures. But what if the James Webb observations are telling us that our observable universe is not typical? If different regions of the universe have different fluctuation spectra, some with enhanced small-scale fluctuations, some with suppressed fluctuations than what we observe, depends on where we are, we might happen to be in a region with enhanced fluctuations, which would explain why we see more early structure than the average model predicts. This wouldn't mean the model is wrong, just that we're observing a non-representative sample. This connects to the concept of cosmic variance, the inherent uncertainty in cosmological observations due to the fact that we can observe only one universe. We can measure the properties of our universe precisely, but we cannot know whether our universe is typical or unusual without observing other universes. The James Webb observations might be revealing that our universe is unusual in ways we hadn't anticipated. The impossible galaxies might be possible after all, just rare, and we happen to be in a place where the rare has become common. This has profound implications for how we interpret cosmological observations. We typically assume that our observations are representative of the universe as a whole. But if there's significant variation on scales larger than our horizon, this assumption fails. We would need to think about cosmology probabilistically considering the distribution of possible observational outcomes rather than a single expected outcome. The James Webb observations would then be telling us about our position in this distribution, providing information about cosmic structure on scales we cannot directly observe. Now let me discuss what the James Webb discoveries might tell us about the anthropic principle and the habitability of the universe. The anthropic principle, in its various forms, notes that our observations are filtered by the requirement that the universe must be compatible with our existence. We can only observe a universe in which observers like us can exist. This might seem trivially obvious, but it has profound implications. If the properties of the universe varied from region to region, or from universe to universe in a multiverse, we would necessarily find ourselves in a region or universe where conditions allow for life. How does this connect to James Webb? If the early universe was more structured than expected, it was also more conducive to early star and galaxy formation. More stars mean more heavy elements, which are necessary for planets and life. More galaxies mean more environments where life might arise. The impossible early structures might have made the universe more habitable than we thought, or they might be necessary for habitability. Consider the alternative. If the early universe had less structure, star formation would have been delayed. Heavy elements would have accumulated more slowly. The conditions for life might have taken longer to emerge. In an anthropic framework, we might expect to find ourselves in a universe or region of a universe where structure formation was efficient enough to produce habitable environments relatively quickly. The James Webb observations might be confirming this expectation. This is a subtle argument, and it doesn't necessarily explain the observations. But it illustrates how the James Webb discoveries connect to deep questions about why the universe has the properties it has and why those properties allow for our existence. Now let me explore what the observations mean for our methods of scientific investigation. The James Webb discoveries present a methodological challenge. When observations conflict with well-established theory, how do we decide what to trust? On one side, we have a theoretical framework, the standard cosmological model, that has been confirmed by numerous independent observations over decades. It makes precise predictions that have been verified. It's the foundation of our understanding of cosmic evolution. On the other side, we have new observations that don't fit this framework. They're based on cutting-edge technology, sophisticated data analysis, and careful scientific work. They've been checked and rechecked. The apparent conflict with theory seems genuine. How do we proceed? The scientific method provides guidance. Observations are primary. If observations conflict with theory, the theory must be revised or replaced. This is how science progresses. But the scientific method also counsels caution. Observations can be wrong. Systematic errors can affect results. New instruments and methods need time to be validated. What seems like a discovery might turn out to be a mistake. The history of science is full of both true discoveries and false alarms. The challenge is distinguishing between them. Several factors favor the James Webb observations being genuine. Multiple independent analyses have confirmed the results. Different research groups using different methods have found the same surprising properties of early galaxies. The observations are consistent with a pattern. It's not just one anomalous galaxy, it's many galaxies with similar unexpected properties. A systematic pattern is less likely to be an error than a single anomaly. The spectroscopic confirmations are solid. When galaxies have been followed up with spectroscopy, which directly measures the redshift from spectral lines, the high redshifts have been confirmed. The galaxies really are as distant as they appear. The telescope is working well. James Webb has met or exceeded its design specifications. The optical quality is excellent. The calibration has been verified. There's no evidence of instrumental problems that would affect the observations. But several factors counsel caution. The observations are new. James Webb has been operating for only a few years. The data analysis techniques are still being refined. Unforeseen systematic errors might yet be discovered. The interpretation involves assumptions. Converting from observed light to stellar mass involves assumptions about stellar populations, dust, star formation history. If these assumptions are wrong, the mass estimates could be wrong. Selection effects matter. James Webb preferentially detects bright, massive galaxies at high redshift. The typical early galaxy might be small and faint, consistent with expectations. The impossible galaxies might be rare outliers that don't represent the early universe as a whole. History suggests caution. Previous claims of paradigm-shifting discoveries have sometimes not held up. The faster-than-light neutrinos at CERN, the BICEP-2 detection of primordial gravitational waves, both turned out to be errors. Extraordinary claims require extraordinary evidence. The scientific community is navigating these considerations carefully. The observations are being taken seriously, but so are the caveats. More data is being collected. Better analysis techniques are being developed. The theoretical implications are being explored. This is science working as it should, neither rushing to overturn established theory based on preliminary data, nor dismissing unexpected observations because they're inconvenient. The balance between openness and skepticism is essential for progress. Now let me consider the deeper philosophical implications of the James Webb discoveries. Science operates on the assumption that the universe is comprehensible, that its behavior can be described by mathematical laws that humans can discover and understand. This assumption has been spectacularly successful. From Newton's laws to quantum mechanics to the standard model of particle physics, we have developed theories that explain a vast range of phenomena with remarkable precision. But is the universe guaranteed to be fully comprehensible? Might there be aspects of reality that exceed human understanding? The James Webb discoveries don't directly address this question, but they remind us of its importance. If the observations lead to a revised cosmological model that explains both the new data and the old, our faith in the comprehensibility of the universe would be reinforced. We would have successfully adapted our theories to new information as we have done many times before. But what if no satisfactory explanation emerges? What if the observations resist incorporation into any coherent theoretical framework? This would be deeply unsettling. It might suggest that our theoretical tools are inadequate, that we need new concepts and methods we haven't yet developed. It might suggest that there are aspects of cosmic history that resist human understanding. I don't think we're at this point with the James Webb observations. There are many theoretical options still being explored, and it's too early to conclude that none will work. But the possibility should be kept in mind. The universe is under no obligation to be comprehensible to minds that evolved for survival on the African savanna. Our scientific success to date might be because we've been studying the easy parts, the aspects of reality that happen to be accessible to our cognitive capacities. The deepest aspects of cosmology, what happened at time zero, why there is something rather than nothing, why the laws of physics are what they are, might ultimately resist human understanding. The James Webb discoveries might be probing this boundary. Now let me explore what these discoveries mean for our sense of our place in the cosmos. For most of human history, we believed we were at the center of a small, young, purposeful universe. The Earth was the center of creation. The stars were decorations in the sky. The cosmos existed for our benefit. Science has progressively displaced us from this central position. Copernicus showed that the Earth orbits the Sun, not vice versa. Galileo showed that the heavens are physical places, subject to the same laws as Earth. Darwin showed that humans are products of natural selection, not special creation. 20th century cosmology extended this displacement to the largest scales. We learned that the Sun is one of billions of stars in a galaxy, and our galaxy is one of billions in the observable universe. We learned that the universe is 13.8 billion years old, and humans have existed for only a tiny fraction of that time. We learned that ordinary matter is only 5% of the cosmic composition, with the rest being dark matter and dark energy that we don't understand. The James Webb discoveries continue this process of cosmic displacement. If the early universe was more structured and productive than we assumed, then cosmic history is richer than we knew. More galaxies, more stars, more possibilities for complexity and perhaps life extending further back in cosmic time than we expected. This is both humbling and inspiring. Humbling because it reinforces how small and recent we are in cosmic terms. Inspiring because it suggests that the universe is more creative, more fertile, more capable of producing structure and complexity than we had realized. The impossible galaxies are not impossible, they're unexpected. The universe found ways to produce them that our theories didn't anticipate. This is a reminder that the universe is larger, stranger, and more wonderful than our limited imaginations conceive. Now let me discuss the practical implications of the James Webb discoveries for the future of cosmology. Whatever the ultimate explanation for the observations, they have already transformed the field. Cosmologists are thinking differently about the early universe, exploring possibilities that weren't seriously considered before. The next decade will be crucial for resolving the mysteries. More James Webb observations will accumulate. The telescope is expected to operate for at least 20 years, providing ever deeper and more comprehensive views of the early universe. As the data grows, statistical analyses will become more robust, and anomalies will either be confirmed or shown to be fluctuations. Other telescopes will contribute. The Euclid Space Telescope, launched in 2023, is mapping the distribution of galaxies over a wide area of sky, constraining dark matter and dark energy. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct wide-field surveys complementing James Webb's deep views. Ground-based observatories like the Vera C. Rubin Observatory will map billions of galaxies, providing statistical power to test cosmological models. Theoretical work will progress. Cosmologists are developing new models, running new simulations, exploring new parameter spaces. The James Webb discoveries have energized the field, attracting attention and resources to fundamental cosmological questions. Particle physics might contribute. If the James Webb observations require new physics, new dark matter candidates, new fields, new interactions, this new physics might have signatures that could be detected in particle experiments. The connection between cosmology and particle physics has always been close, and the James Webb discoveries strengthen it. Gravitational wave observations might help. The LISA Space-Based Gravitational Wave Observatory, planned for the 2030s, will be sensitive to gravitational waves from the early universe. If the early universe underwent phase transitions or other exotic processes that produce gravitational waves, LISA might detect them, providing independent evidence about early cosmic history. All of these observations and experiments will contribute to resolving the James Webb mysteries. Within a decade or two, we should have a clearer picture of whether the standard cosmological model needs minor adjustments or fundamental revision. Now let me bring this exploration to a close by reflecting on what the James Webb discoveries reveal about the nature of scientific inquiry. The James Webb Space Telescope is one of the most ambitious scientific instruments ever built. It cost $10 billion and took over 20 years to develop. It required contributions from thousands of scientists and engineers across multiple countries. It pushed the boundaries of what was technically possible, from the enormous deployable mirror to the cryogenic cooling system to the precision pointing and control, and it has delivered results that no one expected. This is the essence of science. We build instruments to look more carefully at the universe, and the universe shows us things we didn't anticipate. We construct theories based on what we know, and new observations reveal what we didn't know. We think we understand, and nature corrects us. The James Webb discoveries are not a failure of science, they're a triumph. They show that our instruments are powerful enough to reveal new phenomena, that our theories are precise enough to be contradicted by data, that our scientific enterprise is honest enough to take the contradictions seriously. If our theories were vague and accommodating, no observation could ever challenge them. If our instruments were crude and imprecise, we couldn't distinguish between competing explanations. If our scientific culture discouraged questioning established ideas, we wouldn't recognize when those ideas needed to change. The fact that we're having this conversation, that I can tell you about observations that challenge our understanding and theoretical attempts to explain them, demonstrates the health and vitality of cosmological science. The universe has surprised us. This is what we should expect when we explore the unknown. Every major advance in science has involved surprises, phenomena that didn't fit existing frameworks, observations that force theory to adapt. The James Webb surprises may lead to minor adjustments in our cosmological model, a tweak to star formation physics, a modification of dark matter properties, an update to our understanding of initial conditions, or they may lead to revolutionary changes, new physics, new cosmology, new understanding of the universe's origin and evolution. We don't know yet which path we're on. The story is still being written, but we can be confident that the story will be written. Scientists will continue to observe, theorize, test, and revise. The James Webb observations will be explained one way or another. Our understanding of the universe will continue to grow. This is what makes science the most successful method humans have developed for understanding reality. It's not that scientists are always right, they're often wrong. It's not that theories are permanent, they're constantly being refined. It's that the process is self-correcting. Errors are eventually discovered and fixed. Theories are eventually improved or replaced. Understanding advances, step by step, generation by generation. The James Webb Space Telescope has shown us something that shouldn't exist according to our current theories, but the universe doesn't care about our theories. The universe simply is what it is. Our job is to figure out what that is as best we can with the tools and concepts we have. When our tools reveal something unexpected, when our concepts prove inadequate, we don't give up. We build better tools. We develop better concepts. We try again. This is what's happening now with the James Webb discoveries. The observations are unexpected. The explanations are incomplete. But the scientific community is engaged, working to understand what we're seeing and what it means. In a decade or two, we'll know much more. The impossible observations will have found their place in a revised or extended theoretical framework. The surprises will have become established knowledge. And new instruments will have revealed new surprises, continuing the endless process of discovery. This shouldn't exist, but it does. And figuring out why is one of the great adventures of human knowledge. The James Webb Space Telescope has given us a gift, a window into the early universe that reveals our ignorance and challenges our understanding. It has shown us that the cosmos is stranger and more wonderful than we knew. It has reminded us that our theories, however successful, are always provisional, always subject to revision in the light of new evidence. This is the nature of science. This is the nature of human inquiry into the mysteries of existence. We observe, we theorize, we test, we revise, we learn, we grow. The James Webb discoveries are not the end of this story. They're a new chapter, and the chapters yet to come will be even more surprising, even more revelatory, even more transformative than we can currently imagine. This shouldn't exist. But the universe does what it does, regardless of our expectations. Our job is to keep watching, keep questioning, keep trying to understand, and that's exactly what we're doing.